Alright, welcome everybody to another video installment. Um, Today I'll be going over section 1.2 in the textbook. Um, the section is entitled Graphs of Functions, but this section also covers um, graphs of curves, talking about symmetries amongst those curves. So there's two approaches to this section. We can talk about graphs of functions, and then we can just look at graphs of curves. And we'll talk about um, you know we'll talk about the algebraic expressions, and we'll also be comparing or looking at the corresponding graphs of those functions or equations as well. So first thing I want to talk about is graphing functions specifically, and before I get into example 1, I'm going to graph a couple functions by just plotting some points, just plugging specific input values into the function to get the outputs, which would be the y-coordinates. Okay, so here's the idea. Okay, I want to graph functions by plotting points. Now you saw in the previous section that one notation for a function is to write y equals f of x. Okay. And what this implies, when you write y equals f of x, this means xy is a point on the graph of f. Okay, so again, this is saying that when x is the input, you plug x into the expression, you read the output from a table, but x is the input. This is saying that y is the output. Okay, so the input of the function is the first coordinate in the ordered pair, right here, and the output of a function, so like if I plug 2 into the function and get 7, I'll say this in a second, right? Here's a small example. Right? If you plug 2 into the function, the equation or whatever it is, and you end up getting 7, what this is going to tell me is that 2, 7 is on the graph of f. Okay. And if I was going to go ahead and graph that point, let's just talk about how to plot points real quick before I actually start doing a few examples. Okay, so here's a set of coordinate axes. Some people call this the Cartesian axis, or Cartesian axes. And then if I'm going to plot the point 2, 7, I'm going to need to actually go up 7 units. And as a matter of fact, let me do one thing here. I'm going to actually do something like this. Okay, just kind of change how I draw my set of coordinate axes. So I have an x and a y axis. So if I'm going to plot the point 2, 7, I'd actually have to go 2 units to the right on the x-axis and go up 1, 2, 3, 4, 5, 6, 7 units on the y-axis. Okay. And then, okay, for plotting the point 2, 7, okay, again, I plugged 2 into the function, I got 7 as an output, and then on the graph, if I want to convey that information, I would go 2 units to the right, and I would go up 7 units from the origin, oops, which would be about right there. Okay. So the x-coordinate tells you how far from the origin, so right, I'm starting down here, from the origin, the ordered pair 2, 7, that's directions for how to get to the point. So the x-coordinate of 2 means go 2 units to the right, the y-coordinate of 7 means go up 7 units from there. So basically, positive x-coordinates mean you go right from the origin, negative x-coordinates mean you go left from the origin. And then same thing with y values. Positive y values means go up. Negative y values would mean go that number of units down. Okay. Alright, so let's just go ahead and do an example where I actually take the expressions, or what are called the algebraic expressions for a function. So in example 1 it says I'm supposed to sketch the graphs of f of x equals 2 minus 2x, and then I'm going to graph g of t equals t squared plus 2. Okay, so now I'm going to sketch the graphs of these two functions. Again, the first one is the function f of x equals 2 minus 2x. Okay, now there is another way to write this. You could rearrange the terms and write this as minus 2x plus 2. Okay, this is what I'm going to call, or what we're going to call later, as you're going to see, and some of you might have seen this before, but this is a linear function. Okay, so the graph of this is actually going to end up being a line if you're familiar with functions of this type. This line is said to have slope -2 and y-intercept +2. Now, if I didn't know anything about this function, okay, if I didn't know it was already linear and I didn't have any other tricks for graphing it, one thing you could do is you could make a table of function values. Okay, but to make this table, what you're doing here is you're going to select all your x values first, and depending on the function, it might actually take some, it might take some kind of thinking ahead to know which x values to pick. Like if you look at my set of coordinate axes on the left, you're only able to go 10 units in any direction from the origin. Okay, so my x values that I pick have to be between -10 and 10, but I also only have room to go 10 values up and 10 values down on the y-axis. Okay, so it's only really going to make sense for me to pick x values that give me outputs between -10 and 10. So, I think, one thing I could do is I could probably start at like -6. Or wait a minute, not -6, how about +6? So 6, I think, is the largest x value I can use. And I'm just going to go backwards. 4, 2, 0, -2. Okay, and I could pick more x values if I wanted to. Now, the graph of this function is going to end up being a line, so I really only need 2 points. I only need to plug in 2 x values. So using this function up here, I'm going to box it. You're going to start plugging in -2, 0, 2, 4. When you plug in -2, -2 times -2 is 4 plus 2 is 6. When you plug in 0, you're going to get +2. Okay, when you plug in 2 for x, maybe I'll just do one of these. So like how I'm doing this is I'm doing f of 2 now. That's -2 times 2 plus 2. That's -4 plus 2, and sure enough I'm going to get -2. Okay. When you plug in 4, you're going to see that you get -8 plus 2, which is -6, and you're going to see when you plug in 6, you're going to end up getting -10. Okay. So now if I want to plot these points, okay, let me just start boxing these pairs so you can see them. Okay, the first row in the table, -2, 6, saying when x is -2 and you plug that into the function, you get an output of 6, which would be your y-coordinate. That says you should go 2 left, and you should go 1, 2, 3, 4, 5, 6 down, and get this point right here. The next point on the graph, oh sorry, don't listen to me, I should go left 2 and up 6, 1, 2, 3, 4, 5, 6, sorry. There's my first point. Okay, now I would draw in the point that has coordinates 0, -2. 0 means I don't go left or right at all, and I go up 2 coordinates. The next point with coordinates 2, -2, I go 2 right and I go down 2. I get this point. The next one would be 4, -6. That means go right 4, down 6. And you notice that every time I go right 2, I'm just going down 4. There would be the final point. And again, I told you this was a linear function ahead of time. I think I've plotted enough points to convince you that the graph of this function ought to be a line. Okay. So there's the graph of f of x. And you can see this too. If you look back at the equation. Okay, I just boxed it a couple more times. -2x plus 2. You'll notice that every time you go from any point on the line, if you go right 1 unit, you'll notice that you go down 2 units to get another point. And the plus 2 is representing the y-intercept. You'll notice that the graph crosses the y-axis at +2. Okay, now I can do the same thing for the second function. I'm going to do that on the grid on the bottom. The function's t squared plus 2. Okay. So this function, I'm using different notation. The name of the function is g. The input variable I'm using is t, but the function is given by t squared plus 2. Now I'm still going to make a table of values. And again, you might want to be careful, right? There's only certain choices are going to actually have outputs that are going to fit in your in your grid. Now this should really be changed to the t-axis, since I'm using the input variable t. And I believe the only things I'm really going to be able to use here, I think I can go, let's see, you're only really going to be able to use -2, -1, 0, 1, and 2. I could use more, but you're going to notice that if I was to plug 3 or -3 into this function, 3 squared or -3 squared is 9 plus 2 is 11. I'm not going to be able to fit the y-coordinates on the graph. Now I'll do the first value here. I'll do, okay, what's g of -2? That would be -2 squared plus 2. That ends up being 4 plus 2, which is 6. Okay. So when t is -2, g of t is 6. When you plug in -1, you're going to see you get 3. When you plug in 0, you will get 2. When you plug 1, you will get 3. And when you plug in 2, you will again get 6. So again, notice here that this is a function. Each input does have its own output, but it's okay that some of the outputs are repeating. This certainly happens if your function is involving a square somewhere, or can happen if your function involves a variable squared. And now I would plot these points. I would go left 2 units and then up 6. 1, 2, 3, 4, 5, 6. There's a point. Okay. And then I would go left 1 unit and up 3. From the origin, I would go up 2. And so I've already graphed these 3 points right here. Now I'm plotting 1, 3. That means go right 1, up 3. And then finally the last pair, or the last point, is going to have coordinates 2, 6. That means go right 2 and up 6. And if you are familiar with functions of this form, this is what is called a quadratic function. We will study linear functions in a later section. We will also study quadratic functions in section 2.1. Okay, now quadratic functions graphs have the shape of a parabola. You'll see these points actually do fit the shape of a parabolic curve. Okay, so for right now, you know, there are ways to graph linear functions. There are shortcuts. There are ways to graph quadratic functions. There are easy things that you can do to plot them without having to make a table like this. But without knowing any of those tricks or any special characteristics of any type of function, the best way to graph them is really just to start plotting points and then fit those points with the appropriate curve. Okay, so we've seen, I guess, how the connection between inputs and outputs connects to the graph of a function. We've graphed functions by plotting points. Now, going back to the definition of a function, in section 1.1, you determined if something was a function, making sure that each input had one and only one output. Now, what if rather than given a relation through a table or verbally, and you determine if that relation is a function, relations can also be represented by graphs. So, a graph is also a relationship or pairing of elements from two sets, right? So, for instance, if I draw, it's hard for me to do these straight for some reason. There we go. So if I draw a set of coordinate axes, and I say look at this function, or I just draw any random function here. Say this is the graph of f of x, here's your x-axis, here's your y-axis. One thing I want you to notice is that this is the graph of a function. Each input does correspond to one and only one output, and the way that you can see that is by imagining all vertical lines. Okay. Now you'll notice that for this particular function, there's no vertical line that I can draw that's going to intersect the graph more than one time. Okay. Right. Each of these lines represents a different x value. Okay, so like maybe this first line, this is x equals a. The second line is the equation x equals b. The third line is the equation x equals c. Okay, so on these vertical lines, x is always a, x is always b, or x is always c. So focus on this first line right here. Okay, this first vertical line. Okay, notice that that vertical line contains all possible y values, and it only intersects the graph in one place. So that means when x is equal to a, there's one and only one y coordinate. So that would say that this is the graph of a function f of x, or this graph passes the vertical line test. Now, let's maybe draw a graph or a relation. Let's draw a relation in which the graph is not a function. So one way to see this is to maybe look at graphs of circles. Okay. Now, circles will be you'll probably study circles in more detail in pre-calculus 2 or trigonometry. They can be studied earlier. But oftentimes, I'll write it down, the equation for a circle has the form x minus a squared plus y minus b squared equals r squared, where the center has coordinates a, b, and the radius of the circle is r. Okay, so that's the general equation of a circle. And again, this circle would have coordinates a, b, and the radius, or this distance, would be r. Okay. All the points on the circle, so here's a point right here on the circle with coordinates x, y, that will satisfy this equation on the right. If you plug a coordinate into that expression on the left and get the radius squared, that point has to be on the circle. Okay, so that equation is a relation. It relates x values to y values. But what I want you to notice is, if I redraw this now, here's the graph of a circle. Okay, is this relationship a function, or is this relation a function? Well, no. Right, I can find a bunch of lines that intersect that graph in more than one point. Okay, so this, I guess you can say, this graph does not, this relation or the graph of that relation does not represent a function, because the graph fails, and you can just write the vertical line test as the acronym VLT. So this graph does not represent a function because the graph fails the vertical line test. Okay. So next. Okay, what we're going to do now is we're going to learn how to read a graph, find the domain and range from a graph, compute function values, and we're also going to find inputs from outputs. Okay, so I've got this graph on the bottom. Let me resize my window. So here's the graph of a function f of x, and I need to answer these 5 questions, and hopefully I can remember this. F of 2, 2f of 4. Okay, so what I want to do here is part A. I want to find f of 2. Part B was 2 times f of 4. Let me just do one at a time. Okay. So for the first one, if I want to find f of 2 from a graph, remember, what does this notation mean? What is f of 2? This is the y-coordinate of the point with x-coordinate of x equals 2. Okay, so what you're going to do here is, one thing you can even do is just go to, or look at the vertical line x equals 2. You're going to intersect the graph in a single point. And if you go to the left, okay, that point looks like it has a height of 1. So that means that f of 2 probably equals positive 1. Or if you like, the coordinates of that point on the graph that has an x-coordinate of 2, that point has a y-coordinate of 1. Okay. Now, the next part B, is 2 times f of 4. Okay, so part B, I need to find 2 times f of 4. So what you're going to do is there's really a multiplication going on here, and you actually have to find f of 4 first. So this will be 2 times whatever f of 4 is. Now I'm going to do the same thing. If I want to find f of 4, that's the y-coordinate when x is equal to 4. So if you go to x equals 4, you go up to the corresponding point on the graph. Okay, so that's the point. What I've done is now, this is the point on the graph that has an x-coordinate of 4. And if you go straight to the left, it's not exactly true, but it's pretty close. Looks like that point has a height of 5. Okay, so what that means is that if there's a point on the graph with coordinates, okay, this point up here has coordinates 4, 5. Let me rewrite that. Okay, that means when the x-coordinate is 4, the y-coordinate is 5. That is exactly what f of 4 is. So this becomes 2 times 5, which is going to give you 10. So we're basically just finding twice the function value f of 4, which is twice times 5, which is 10. Okay, now part C. Part C wants me to find all x such that f of x equals 5. Okay, so part C, I want all x such that f of x equals 5. Now notice this time I'm given the function value of 5. Right? This is notation for the y coordinates. Okay, so this time what you're going to do, you're going to find 5 on the y-axis, and you need to find all points on the graph that have a height of 5. And you're going to notice there's only one such point, and the corresponding x value can be found by going straight down to the x-axis. Okay. And there's only one point with a y-coordinate of 5, and the x-coordinate is 4. So f of x equals 5, 4. Now there might be multiple x values, but in this case there's just one. Okay, the answer would be x equals 4. You saw in the previous problem that we found 2 times f of 4, and we knew that f of 4 was 5. Okay, now I need to do part D. So all x such that f of x equals 2. Okay, so now I want to find, for part D, it's all x such that f of x equals 2. And again, this is notation for a y-coordinate. That's what f of x's are. We need to find the value of x when the y-coordinate is positive 2. So again, this time I'm going to come to the graph. I like to draw horizontal lines. So here's y equals 2. If you draw a horizontal line, you're going to notice you intersect the graph in 3 places, actually. So there's 3 points on the graph with y-coordinate 2. And if we go straight down to the x-axis from these points, the answer to this question, f of x is equal to 2 when, now if you look on the x-axis, those 3 points have the x-coordinates of -2, 0, and 3. Okay, right, -2, 0, and 3 on the x-axis. Okay, so that means that if I plug -2, 0, or 3 into the function, whatever the function would be, the graph tells me that the y-coordinate has to be positive 2. Now finally, I believe we need to do part E. We are now finding the domain and the range of this function. Now, the domain, this is the set of all x coordinates. Okay, so I'm going to do that first. And what I want you to focus on is the x-axis goes horizontally from left to right. So as you're reading the graph, the domain would be all the x coordinates, but notice the graph moves continually from left to right. So if you focus on the leftmost point and the rightmost point, okay, those are the smallest and possibly largest values in the domain. Since the graph moves continuously from left to right, the domain is going to start at, so if you follow me from this point on the farthest left, that's where the domain is going to start on the x-axis. Okay, that's not going to be included though. The domain's going to move to the right until I get to positive 4. That's the farthest rightmost point. Now, look at the endpoints of this function. What I want you to notice about the endpoints is over here on the leftmost endpoint is an open circle. That means it is not on the graph, so whatever x-coordinate I get on the x-axis, or x value, that is not in the domain. Notice though this point is a closed circle, that means that is a point on the graph. Okay, so 4 would be included in the domain. Now, I believe, I have to erase this, it looks like, I think each tick mark represents half a unit. So the domain starts at -3.5 and moves continuously to the right until I get to positive 4. And now, I'm writing the domain in interval notation. I'll write it down in set notation in a second. Okay, but since negative 3.5 is not in the domain, you're going to write a parenthesis. And since positive 4 is in the domain, you're going to write a closed bracket. Parentheses means to exclude a value. Brackets mean to include a value. And when you write an interval like this means the domain is all numbers greater than negative 3.5, but that are also less than or equal to 4. So another way to write the domain here would be, you could write it, it's the set of all x such that x is bigger than 3.5 and less than or equal to 4, if you were going to use set notation. Okay, now the range, this time, the range is the set of all y coordinates, correct? So, y coordinates, right, the y-axis goes vertically. You're going to look for the lowest point, and then move to the right. Draw an open circle. That's where the range will start. Again, since the graph moves continuously from the lowest to the highest point begins at 5. And then let's just say this is about negative 2.25 down here. Or sorry, negative 2.5, my bad. Okay, that's about negative 2.5. The graph goes continuously from its lowest to its highest point. So, the range would start at negative 2.5, go up to positive 5. Negative 2.5 is not an output because of the open circle, but positive 5 is an output because of the closed circle, so that would be included. You can also write the range like thusly. The range can be written as the set of all y, so that y is greater than negative 2.5, but less than or equal to positive 5. Okay, so that's the interval notation and set builder notation for the domain. Here is the interval notation and set builder notation for the range. Okay, next thing I want to do is talk about symmetry in graphs. Now, moving forward, when I'm talking about graphs, I'm going to be just talking about any graph. It doesn't necessarily have to be a graph of a function. So, right, it could be the graph of a circle. It could be either the graph of a function or not. Okay, and we're going to talk about various symmetries in those graphs with respect to the y-axis, x-axis, and the origin. Okay, so this is just about looking at the equation or relationship between the points on a graph. And again, that can be displayed in two ways. We're going to do this by, as I do things algebraically, right? Any equation or relationship between x and y has a corresponding graph. That graph may or may not be a function depending on if it passes the vertical line test. Okay, now after I talk about symmetry in general, I will then talk about symmetry as it pertains to functions alone. Okay, so there's three different kinds of symmetry. Symmetry with respect to the y-axis, the x-axis, and the origin. Okay, so a graph is symmetric with respect to the y-axis if for every point that's on the graph with coordinates x, y, okay, so take any point on the graph, and I want it to be symmetric with respect to the y-axis. Okay. Then in that case, the point minus x comma y, it has to also be on the graph. Okay. So pictorially, here's what's happening, or graphically, let's say. Okay, so here's my set of coordinate axes. There's an x-axis and a y-axis. And, okay, I'll just draw the most standard graph that I can think of that's symmetric about the y-axis. Okay, it could be a circle, okay, but I'm just going to draw something that's in the shape of a parabola. Okay, so again, it doesn't necessarily have to be a function, right? I could be talking about, I'll even talk about like a semicircle, or I can talk about an entire circle. And what you notice here is take any point on the graph with coordinates x comma y. Maybe I'll do that over here on the circle as well. And what you're supposed to be able to do is, if it's symmetric about the y-axis, you should be able to reflect this point over the y-axis and obtain another point on the graph. Okay. So if this graph is symmetric about the y-axis, if I start with the point xy, you'll notice that this point on the left still has the same y-coordinate. But if this is x and you reflect it over the y-axis, this is going to become the value minus x, right? So if I start with 2, that's going to become a minus 2. And notice the y-coordinate, oh shoot, I don't want to write minus 2. That's minus x in this part, in the general case. Okay. So that's what's happening graphically. Okay, basically it just means if you switch the sign on the x-coordinate and keep the y-coordinate the same, a graph that's symmetric with respect to the y-axis, you would have, basically both those points would be on the graph. Okay. And the same would be true over here on the left in the circle. If you reflect over the y-axis, again, you're going to get the point minus x comma y. I know my circle doesn't look very symmetric, but that is supposed to be a perfect circle centered at the origin. Okay, so again, you'll notice that those 2 points, if you reflect over the y-axis, the y-coordinate is going to stay the same, and you're just going to change the sign on the x-coordinate. In any graph that's symmetric about the y-axis, changing the sign on the x-coordinate is going to also give you another point that is on the graph. Okay, so that's symmetry with respect to the y-axis. Now, for any given graph, there's also a corresponding expression or relationship between x and y that would give you the points on the graph. So I'll show you in a second how to look at an equation and determine the symmetries without even having to look at the graph. Okay, so second kind of symmetry is I'm going to talk about symmetry about the x-axis. Okay. A graph is symmetric with respect to the x-axis if for every point xy on the graph, it turns out that the point x minus y is also on the graph. Okay. And again, graphically, what's going on here? Instead of x, there's the y-axis, there's the x-axis. Look at any graph you want. Again, it can be a circle, an ellipse, it can be any sort of just wild graph that you can think of. It doesn't have to follow any rules. It doesn't have to pass the vertical line test. You can draw anything you want. For instance, I could draw a parabola opening to the right. Okay, so here's an example where I have a graph, and it's not a function. This does not pass the vertical line test. Now, if you take any point on this supposedly symmetric with respect to the x-axis, I'll use a different color there, if you don't mind. If anybody has any issues with any of the colors that I use, just make sure you let me know. So if I take the point with coordinates x, y, now this time, notice there's a symmetry about the x-axis. You can kind of see how over the x-axis the graph is a mirror image. And that means if I reflect that point through the x-axis, okay, if I mirror it over the x-axis, you're going to end up with another point on the graph, and you'll notice that the x-coordinate has not changed because you're on the same vertical line, but you'll notice the y-coordinate has changed, again, by sign. Okay. So basically, a graph is symmetric with respect to the x-axis if changing the sign on the y-coordinate does nothing to the graph. Or, I shouldn't say does nothing to the graph, but changing the sign on the y-coordinate always gives you another point on the graph. Okay, or we'll see this in a second. In terms of equations, This just means that if you replace y with minus y in the original expression and simplify, you get the original expression back. So I'll show you that in just a minute. I'll show you the algebraic way to determine symmetries. Okay, third kind of symmetry. Again, these you don't need to necessarily print or use these handouts. This is just something that I use to kind of summarize terminology in the textbook, formulas. I did try to do examples that are for the most part similar to ones that you'd find in the textbook. Okay, a graph is, so third type of symmetry, this is symmetry with respect to the origin. Okay. Now, a graph is symmetric with respect to the origin if for every point x, y on the graph, the point, now maybe this time first I want to draw a picture of a graph, and I want to actually show you what symmetry with respect to the origin would look like first. So here's a function, actually sorry, I should not say function, here's just a graph. Okay, again, these don't necessarily have to be graphs of functions. Now, symmetric about the origin means if I take a point on the graph, say with coordinates x and y, could be whatever the coordinates are, reflecting that point through the origin actually means if I draw a line from that point that goes through the origin, okay, if I always intersect the graph again, or if the graph intersects that line with another point, okay, and that happens for every point on the graph, that means I have symmetry with respect to the origin. Okay, so it means I start at the point with coordinates x, y. Again, I'll just show you one more time. And if I draw a line through that point in the origin and I intersect the graph again, that graph has symmetry with respect to the origin. And it turns out there's actually two kinds of reflections going on here to get there. You can reflect once over the y-axis. So that's like changing the sign on the x-coordinate. And then you'd be reflecting over the x-axis, which is going to change the sign on the y-coordinate. Okay. So, a graph is symmetric with respect to the origin if for every point with coordinates x, y on the graph, the point minus x minus y is also on the graph. Okay, and then now let's see some examples. We'll look at expressions or relationships, equations involving x and y that have corresponding graphs, but without actually graphing the functions, we should be able to determine algebraically the symmetries. Okay. Alright, so example 3 is going to be, again, how to determine symmetries of graphs by examining the actual equation or relationship between x and y that would give you the points that are on its graph. Okay, and again, there's three types of symmetry: x-axis, y-axis, and the origin. Now, as I actually do this algebraically, I am going to also be graphing each of these equations in Desmos so that we can just get a visual confirmation of the symmetries. Okay, so first one, some of these graphs might look pretty familiar once I actually graph them. And again, we're going to talk about that later. Some of these might also actually be equations that do give functions and others might not be. Okay, so 2x squared minus y minus 4. So now what if I want to do, and actually I think, let me actually start off by doing y-axis symmetry. Okay. Now remember, y-axis symmetry means that xy on the graph implies or means that minus xy is on the graph. Okay? That means you reflect anything that's already on the graph gets reflected over the y-axis. You get another point on the graph that changes the sign in the x-coordinate. Now, when you write an equation, now focus on the equation. When you're writing 2x squared minus y equals negative 4, points on the graph are coordinates xy that satisfy this equation. So I'm already saying, in a sense, that just by looking at the equation as written, x and y are satisfying the equation. So what I have to show, or do, is I actually have to, now, in the equation, I am going to replace x with minus x and simplify. Okay, and if I get the same expression back after simplifying, that is going to tell me that the point minus xy also satisfies the equation, so that would also be a point on the graph. Okay, so now let's do that. It's going to become 2 times minus x squared minus y equals negative 4. Okay, so you're taking the expression from above, you're replacing x with minus x. Now what you're going to notice here, I'm using implication arrows every time I simplify an equation. Anytime I do another step, I use implication arrows. Anytime I'm simplifying a given expression, though, so an expression is something that does not already have an equal sign in it, I can use string of equalities, and you'll see me use implication arrows when I'm simplifying equations, and you'll see me use equal signs when I'm simplifying expressions. Okay, so right now I'm simplifying this equation. Now look at the minus x squared here. Focus on that. That's the only thing I'm going to be simplifying. Okay, again, think PEMDAS when you simplify, or when you simplify, you always use PEMDAS starting with P, and when you solve, you go in the backwards direction. So minus x squared, you have to square the negative and square x. So you would be getting 2. That minus x squared is going to become just an x squared. And then the rest of the expression is still minus y equals negative 4. Okay. Now, notice that is, you might have to do another simplifying step, but that is the exact same equation that we were given at the beginning. Okay, so you would say this implies the equation has y-axis symmetry. Okay. Now, I can do the x-axis. Okay. Now remember, x-axis symmetry is, a graph has it, if xy is on the graph, that implies that, now this time it's interesting, when it has x-axis symmetry, you actually change the sign on the y-coordinate, and that resulting point is also on the graph. So what you're going to do is you're going to again take the original expression up here, but you're going to this time replace y with minus y and simplify. Okay. So that would make, if you look at the original expression now, that would be, the first part would not change. You'd have 2x squared. Okay, minus, but what you have to do is you have to actually replace y with minus y, and you still have that that's equal to minus 4. Okay, so I took the original equation. Okay, that equation represents a graph, and For the graph to have x-axis symmetry, I have to replace y with minus y. Now what I'm going to do is I'm going to simplify this expression. Notice the subtracting a negative y is going to become a plus y equals negative 4. Okay. Now that is not there's no way that I can simplify this equation. Okay, notice the right-hand side is negative 4. There's no way that I can simplify the left-hand side to be the 2x squared minus y. Okay. So notice that is not the original expression. I know, I'm just going to write like a, I'll just write like an x. I didn't get the original expression back. So the graph does not have y-axis symmetry. Okay. Sorry, that should be x-axis symmetry. Okay. I replaced y with minus y in the expression. I simplified. There's no way to get the original expression back. It does not have x-axis symmetry. Okay. Now, so we have y-axis symmetry. We have x-axis symmetry. I'm going to just get rid of this work here for the y-axis symmetry part. Okay, so what I did here, you'll notice the screen has changed. I just wrote up all this work here for checking the origin symmetry. So for a graph to have origin symmetry, xy on the graph means minus x minus y or implies minus x minus y is also on the graph. So that means minus x minus y should satisfy the original expression. I replaced x and y with minus x and minus y. Right. I simplified and again got 2x squared plus y equals negative 4. Again, notice that is not the same as the original. So what do I have? The graph does not have origin symmetry. Okay. So the only symmetry it has is y-axis symmetry. Okay. Now, if I go online, find Desmos. Okay. Now, what you can do in Desmos to get the power there, so I just typed in 2x to get the power. You can come to Desmos.com. Actually, let me show you that. I'll come to the original website. Okay, so I came to Desmos.com. This is graphing, a graphing tool, a free online graphing tool. You can click the Start Graphing tab right there. And then you can type you can type the expression of a function in, or you can just type an equation in that gives a graph. So here I'm going to type in the 2x squared, or I'm going to enter the equation from part A. You would first type 2x, then you'd hit the Shift 6 key. That's like, I don't know what to call that. It's like Shift hat. You can type in the squared. You can arrow out of the power. I think this is pretty self-explanatory. I think we had minus y, and then we had an equals minus 4. Okay. Now, after you type that in, you're going to get the graph. Okay, that corresponds to that equation. Now you're going to notice that this graph is actually a parabola opening upward. That expression can actually be solved for y to get a quadratic equation. And you'll notice that the point 1, 6 is on the graph, but so is the point minus 1, 6. So it has y-axis symmetry because if you change the sign on the x-coordinate, you still get another point on the graph. Now if I look down here, where's the x-axis? Let me zoom out a little bit. Okay, so you see the x-axis here. Here's the origin. Or there's the origin at 0, 0. And then now, you'll notice like the point 0, 4 is on the graph. but the point, if you reflect that any of those points over the x-axis, you will not get any other points. So this clearly does not have x-axis symmetry, and it doesn't have any origin symmetry either. You can see that, right? Here's a point on the graph up here. If I draw a line through the origin, it's not going to intersect the graph again. Okay, sorry, that's a terrible line. I'll probably draw something like that more. Okay, but there's no way to intersect the graph by reflecting through the origin or over the x-axis, so that only has the y-axis symmetry. Okay. Now, there's two more examples. Let's see if I really... in a similar manner, you could do these other two. I'll just maybe let you check them on your own. Oops. Sorry. Okay, so there's examples 3 parts B and C. You'll see that this one has this one in part B, you're going to see that this has all types of symmetry when you work it out by hand, or when you go into Desmos and look at the graph. It's actually the graph of what's called an ellipse. The reason it's having all types of symmetry is because of the x and y variables both being squared. This one has none of the types of symmetries, none or no symmetries. Okay, and you can see that the easy way to see that is that, okay, the x term and the y term both have an odd power of 1. Okay. In the first one, we only had y-axis symmetry. Notice that the only variable that has an even power is x. Y has an odd power. I would be careful not to always just use that reasoning. There are times where you have more complicated equations than these these 3 that I've given you here. Okay. So moving on. Okay, I want to keep the video shorter. I'm already running on almost 60 minutes. Okay. So even and odd functions is the next thing I want to talk about, and this does again pertain to symmetry, but instead of just talking about the symmetry of graphs coming from equations whose graphs may or may not be functions, now we're going to talk about functions and specifically their graphs. Okay, so there are 2 terms here. We're going to learn about what are called even functions and odd functions. And there's, you'll notice that above with the symmetries, a graph can have no symmetries, it can have all the types of symmetries, it can have one and not the other 2. There's basically any possibility there. And when I talk about functions though, a function is either even, odd, or it's neither of the 2. Okay, so it's literally either even, odd, or neither. Okay, there's no other possibilities. Okay, when I talk about graphs though, you can have all the symmetries or none of the symmetries or any combination of the symmetries. Okay, so even and odd functions. I'm going to first, for an even function, give you a very familiar even function. You'll also notice that I'm choosing a function that has an even power. Okay, so f of x equals x squared. If your terms just contain powers of x, okay, there's an easy way to tell if it's an even function, if it's a polynomial. Again, if it's a fraction or a quotient, you have to be a little bit more careful. Now, what does the graph of f of x equals x squared look like? Also, that's way too big. Okay, so here's the graph of f of x equals x squared, and again, you can see that symmetry about the y-axis. You know, this is called the implicit form. You could also write this as y equals x squared, and then on the left side you have the function notation. Okay, so you could still talk about if you write y equals x squared, I could just, talk about the symmetries that I talked about before, x-axis, y-axis, and origin symmetry, and I can check algebraically, or, you can use Desmos to verify. That would only have y-axis symmetry, and it would not have the x-axis or origin symmetry. Okay, now an even function says that f of minus x equals f of x. Okay. Now, let's think about what that is saying. Okay. Both of these function notations correspond to points on the graph. Okay. This is saying that minus x comma y is on the graph. So both of these, let's say, are equal to y. Right? F of minus x and f of x are equal. Let's say they equal y. This is on the minus x minus y is on the graph. F of x, if that also equals y, that's saying that that's saying that x comma y is on the graph. Okay, so when you say f of minus x equals f of x, that is basically conveying the same information that a graph with y-axis symmetry would possess. Namely that, writing y equals f of x means xy is on the graph, but y is also equal to f of minus x, which means minus xy is on the graph. Okay, so any even function that satisfies that property has y-axis symmetry. Okay, so basically and look at f of x equals x squared, what do you notice? You will notice that f of minus 2 and f of 2 are the same. Okay, I'm running out of room there. Okay. So, and that would be the same for, f of negative 3 is f of 3. And that's because if all your function is doing is squaring the input, the sign does not matter. Okay. So that's what an even function means. The sign on the input does not matter. Okay. You get the same output whether it's positive 3 or minus 3. And that gives you y-axis symmetry. Okay. Okay, I can talk about origins, in contrast with an even function, there's an odd function. Okay, a prototypical one that's pretty simple to see is x cubed. Okay, and I've again already drawn this picture earlier. F of x equals x cubed's graph has this shape. It has positive outputs for positive inputs and negative outputs for negative inputs. And okay, if you look at the graph of this function, okay, it does have symmetry through the origin. We'll talk about that in a second. But graphically, here's what's going on. If this is x and this is minus x, this point has coordinates x, f of x. Okay, this point over here has coordinates minus x, f of minus x. Okay, and to be an odd function, it's just saying that f of x and f of minus x are opposite in sign. Okay, so again, if I say y is equal to f of x, okay, so that's saying that x, y is on the graph. Okay. Now, what does it mean to say that f of minus x is equal to minus f of x? That's equal to, if y is equal to f of x, minus f of x is minus y. So that means minus x minus y is on the graph. And if you go back what I said before about the symmetries of graphs, if a point is on a graph, x, y, and the corresponding point minus x minus y is always also on the graph has origin symmetry. Okay, so odd functions are really just saying there is origin symmetry. Okay, and x cubed is your prototypical one. For example, if I do f of 3 here, I'm going to get 3 cubed, which is 27. If I do f of negative 3, I'm going to get minus 3 cubed, which is negative 27. And you'll notice that f of negative 3 is minus f of 3. So basically, one way to think about this is for odd functions, the negative sign can be brought out front, and for even functions, the negative sign can be thrown away and you still get the same output. Now, again, you can see this graphically. If you have a graph of an even function, you'll see the symmetry over the y-axis. If you're looking at the graph of an odd function, you'll see the origin symmetry. But what if I am just given a function and I don't have its graph? How can I determine even and odd? Okay, so example 4, even, odd, or neither. I think I might do the first one, and I might actually do another one that is not already on this page. Maybe I can give you the answers to B and C here, but I want to do part A. Maybe I'll do part A, B, and maybe make up another one for you. Okay, but here's 3 functions, and I'm going to make some room. I want to know if these functions are even, odd, or neither. Okay, so by the way, a function is either it's either even, odd, or neither. It can't be even and odd. It can't be, of course, it can't be even and neither. But a function cannot be even and odd at the same time. Okay, just like a number. You know, the number 3 is not both even and odd. It is strictly an odd number. Okay, so I'm going to write these both down. If the function's even, what has to be true? F of minus x has to equal f of x. If a function is odd, what has to be true? F of minus x has to be negative f of x. Okay, and there's only 3 things I really need to be computing here. Okay, when I'm going to determine even, odd, or neither, okay, of course I want to know the original function. I also want to know what f of minus x is. Okay. And then the other thing I want to know is what minus f of x is. Okay, why those 3 things? Look at everything that's written down on either side of an equality here. The only thing that you see is f of minus x, f of x, and negative f of x. And determine even, odd, and neither, I just have to compare those together. Okay? Right, so I'm going to compare these 2 together to know if it's even. Okay, I'm going to compare these 2 together to see if it's odd. Okay, now f of minus x is going to be obtained by replacing all the x's in the expression with minus x. Right, this is going to get plugged in for both of these x's. Now you can simplify. You're going to get 3x squared minus 4x. And how does that compare with f of x? Those are 2 different functions. That means f is not an even function. Okay, so I'll write that on the bottom. F is not even. Why? F of minus x does not equal f of x. Okay, now I'm going to take a look at odd. Okay, and actually, let me make some more room and write this a little smaller on the bottom. F is not even. Right? F of minus x was not f of x. Okay, now come over here and I'll calculate minus f of x. That's just the negative of the original function. The negative can be distributed. I get minus 3x squared minus 4x. Now again, you're going to be comparing these 2 together. One is f of minus x and one is minus f of x. The only way that a function can be odd is if those 2 are the same. Those are not. Those are 2 different functions. F is not odd, f of minus x does not equal negative f of x. Okay, so what's the answer for that one? It's neither. Okay. Okay, so f is neither even or odd. Okay, so I want to do one more. I want to do part B. Or maybe I don't even want to do part B. Let me do like part A.5. I want to do one that's a little more, I guess, difficult than these two, or maybe different is the better word. Now, I will tell you this though. You can check these on your own. This does end up being an even function. Notice that this is a polynomial. If you consider 2 to be 2x to the 0, then this is an even function because it's a polynomial where each power of x is even. You could probably, looking now at part H, guess this is going to be an odd function. Right? It's a polynomial and each term has a power of x that's odd. Now, the reason I want to do another example, maybe I'll just call this part D, is if you have a quotient or a rational function where you have a numerator and a denominator, then it's a little more complicated. Okay. It's not just about which powers, whether the powers of x that are appearing are even or odd, or okay, it's just not that simple. Okay, so what if I want to look at f of x equals 2x squared plus 3 over x cubed minus x, and I want to know if it's even, odd, or neither. And again, just another reminder, even functions have what property? F of minus x, or g, or h, of whatever the name of the function is. Make sure you're using make sure you're using the right letters, right? If I'm working with g of x, I should be using g. Right? An odd function has what property? Again, letter doesn't matter. If the function's g, it should be g of minus x equals negative g of x. So for my function, I'm going to compute three things. I need to know f of x, I'm going to know minus f of x, and I want to know, oops, hold on. I usually do it in this order, my bad. I do f of minus x to know if it's even right away. And then once I do that, I want to know what minus f of x is to see if it is odd. Okay, so f of x, that's just the original function. Okay, f of minus x, you're going to have to replace all the x's with negative x. So in the denominator, you get minus x cubed minus negative x, like so. And then you can simplify. The numerator remains 2x squared plus 3. Squaring minus x gives you x squared. The denominator, minus x cubed, is actually negative x cubed. There is a difference with or without the parentheses. Minus negative x becomes a positive x. Okay. Now, on first glance, just want you to notice it's not so obvious that these two are how they're related. They have the same numerator. Okay. I guess you look at the denominator though, they have the same numerator but they have different denominators, right? One has x cubed minus x in the f, and one has minus x cubed plus x. Okay, so comparing these two, that's going to tell me that f is not even. Okay, again, that's because f of x is not the same as f of minus x. Okay, now I'm going to compare f of minus x to minus f of x. Now, minus f of x is just putting a negative out front. Now, if I'm trying to show that's the same as f of minus x above, the second one, the one I've computed in the middle, you'll notice that the numerators are the same, 2x squared plus 3. The only way that minus f of x and f of minus x are the same is if you distribute the negative sign you have a choice. You can distribute it to the top or bottom. You want to keep the top the same. Okay, but that negative can be brought to the denominator and then distributed. So I'd get minus x cubed plus x. And you'll notice that these two are now identical. Okay, I've ran out of room. Let me come up here. That implies that f is odd. Okay, I just showed that f of minus x is the same as negative f of x. Oops, I'm trying to write in a spot that has the page. There we go. So it's odd because f of negative x is negative f of x. Okay, now again I gave you the answers to parts B and C. Part B was an even function, and part C was also an odd function. Take a look in the textbook. They might do these examples in a slightly different way than I do it, but for the most part it's pretty similar. Alright, the last thing I want to talk about is equations representing functions. And the reason I want to do this is we talked about symmetry in graphs. Okay, and remember, some of those graphs are functions and some are not. We talked about how to use the vertical line test to look at the graph and know if it's a function. I didn't really talk about looking at an equation involving x and y and talk about how to know if its graph will be a function or not. We did talk about how to determine the symmetries, and we saw how to determine symmetries of functions, but now I want to talk about how to determine if equations represent functions. I'm going to do this rather quickly. The video is already on 77 minutes, but just make sure you read this note. Given an equation involving x and y, you can see if the equation gives y as a function of x by solving for y. Okay, so each of these equations you're going to solve for y, and then looking at that equation, use the resulting equation for y to make sure that each input x gets assigned one and only one output value, y. Okay. Now I'm going to solve all of these in the next slide here for all of you to see. Or I'm going to solve all of these for y. Okay. Okay. So what I did here is, again, to know if an equation represents a function, meaning its graph, the graph of that equation would pass the vertical line test, you're going to solve each of the equations for y, which I've done in each of the three examples. Now I want you to look at, okay, for the first problem, y is equal to 7 minus 3x over x squared. Okay, so what this means is any x value that I plug on the right hand side is going to only correspond to a single y value. Okay, that again, you're going to notice that this has something to do with the power of y being an odd. Okay, part B, I solve for y by adding 2 and subtracting 4x on both sides, dividing by 2x in the next step, and then the third step is by taking the cube root of both sides. Again, there's only a single cube root, so there's no need for a plus or minus on the right hand side of the equation. So again, each x value gives you a single y value. That means for that equation, y is a function of x. And finally, part C, notice this time though y has an even power. You add 2x to both sides, divide by 3x cubed. Okay, but then in the next step after what I've boxed, you have to take the fourth root of both sides. Okay, but there are actually two even roots of any number. Any positive number, even fourth roots. So this is why you need a y equals a plus or minus the fourth root. of 3 plus 2x over 3x cubed. Now this time, that means that because of that plus or minus, y is not a function of x, because there are now x values, or almost every x value is going to be assigned to more than one y value. So right, pick a single x, plug it into the right hand side, that's going to give you two y values, a positive and a negative value. Okay, so that will that original equation will not represent a function. So ultimately what you want to do is solve for y, and for certain equations that's going to lead to a single y value for each x, and for other equations it's going to lead to multiple y values for a given x. Okay, again, sorry this video is pushing 80 minutes. In the future I will try to pause the recording much more frequently and do a lot of writing behind the scenes, try and keep these videos shorter, and I'm sure some of you will be fast forwarding through the video just to see my work and tune me out a little bit, which is okay. Thanks for tuning in, and let me know if you have any questions. Make sure you join the Zoom sessions and you're communicating with me through Canvas, getting the homework assignments done. Have a great afternoon.